But yeah, the whole idea is to just try to get students a little bit more interested in research and, what the university does outside of their classroom work, which is kind of the obvious, right? So the story that I'm going to be telling you today is by and large not my own work. This is supposed to more or less be like an introduction to the field. Like, what kind of mysteries can quantum chemistry solve? Then at the very end, I've got some 5 slides, 4 of which are really just 4 versions of the same slide that, kind of like delve a little bit into like where our contributions are. But for the most part, I just want to be really clear about that right from the beginning. This is not exactly my work. This picture here, however, is my work, and I'm really proud of it because mostly it's so beautiful. If you, in order to understand why it's so beautiful, the rainbow colors, you'd have to know something about complex numbers, which I'm just not going to get into today. There's just not enough time. This talk is also a little bit of a kind of a unveiling, sneak preview, crash test of some new presentation technology. So for instance, this whole presentation right now, if I get their keystrokes right, it's this. Yeah, you can see it's running in a web browser. So, and it's like, why would you write your own, web-based, why would you write your own web-based presentation software? It's got everything to do with the animations, right? Like, why am I not just doing, if I wanted it to be on the web, why am I not just doing it in Google Slides? It's got everything to do with the animations, of which this is, let me just go ahead and get rid of that because that's ugly, right? Of which one of the animations is this here. And I'm not going to be talking at all. Let's see, hold on. My mouse goes off that side. It's got to come on this side. I'm not going to be talking at all about this particular animation. That's not really the point. The main point here is that this entire animation was made with only 50 lines of code. Now, I know that might not mean a lot to some people, but if you've ever done any coding, you realize it usually takes you about 10 lines just to set up your variables. And so this is only about 5 times as long as that. So the whole point here is that the whole design principle of the animation code was to let normal people make really cool animations without killing themselves to keep track of all the minutia, right? It does all the time stepping. Like basically all you have to really do is define the physics you want. It interpolates everything else that you need in order to, I don't know, watch how particles move inside of a water wave. And so if you hit this QR code, did it actually work? Were you able to hit it from your seats? Okay, that's why I made it enormous, right? So, and then you can even pass it to your neighbor, right? Once you're on. So if you manage to hit this QR code, this is a hyperlink, so you can actually check out the code for that if you want. Okay, so now kind of on with the show. The focus of this talk is going to basically be like, how does quantum mechanics underlie vision, right? So it's kind of a wild thing, right? Like we all see. I mean, it doesn't get much more tangible than that unless you're actually talking about the sense of touch, right? So we all see, and then quantum mechanics is like this mystical thing that, with the exception of a few people who I've seen have been in my classes or in my department, it's like this thing that's like out there that you hear about. It shows up in expressions like it's not quantum mechanics, and then other than that, you never hear about it and you have no idea what's inside that box, right? So, where is the quantum mechanics? How does quantum mechanics actually contribute to this thing that we do every day, all the time, right? So first, let me give you a much higher level overview of how we see that doesn't actually even rely on quantum mechanics. So it's just even more basic. So here's this is a very quick and dirty rendition of a light bulb. The operative thing inside of a light bulb is a very thin wire in which you run an enormous current for the thickness of the wire that's in there. I mean, these light bulbs are going out of style by, when I give this talk 10 years from now, nobody will have seen one of these incandescent bulbs anymore. But that's how it works. There's this tiny little wire in there. And for the size of the wire, you're running this enormous current through there. It's heating it up to white hot and it's emitting light. Okay. But what that really means, when you're heating it up to white hot, what you're doing is you're causing everything inside that wire to move, including the electrons. Now, when the electrons move, they start jiggling back and forth. They start disturbing the electromagnetic field in their vicinity. And having to do with things that I'm not going to really get into, those disturbances last. They don't decay as you get farther away from the light bulb, other than the fact they get spread out into more space, which is why things appear dimmer when you get farther away. But fundamentally, the energy doesn't go anywhere. The energy stays in that external space. It's emitted as these waves, these little jiggles of the electromagnetic field that go out away from the jiggling electrons here. Now, you've got electrons on the back of your eyeball as well. So that little jiggling field hits the electrons on the back of your eyeball, causes the electrons on the back of your eyeball to jiggle. And once those electrons start jiggling, magical chemistry and biology can happen, right? That's as far as I'm going to take you, right? I don't know anything about the biology that happens after that, right? As soon as the electrons on the back of your eyeball start wiggling, that's more or less when I'm done, right? But that's how you see, that's how a signal gets transmitted from one place to another, and that's how you pick it up. I am going to be focusing the talk on this event right here, right? What is the quantum mechanics going on that describes this event right here when something inside your eyeball picks up on the electromagnetic radiation that came from somewhere else, anywhere else. Okay, but I can't do this without introducing you to at least one technical concept, right? Nothing in physics moves forward, like literally and pedagogically, right, without the concept of energy, right? And in particular, we have to deal with the concept of potential energy and kinetic energy. So first, let's just talk about kinetic energy. That's the easy one. It's the energy of motion. So this is kind of really harder to navigate that. There we go. All right, so we got this thing, and this is not unintuitive. What's happening here? It's a ball or a coin rolling back and forth in a dish. It rolls uphill, it stops, it rolls back, it stops, it rolls uphill, it stops. And when it's at the bottom is when it's moving the fastest. So pay attention to that really quickly. It's moving the fastest when it's at the bottom. That's when we say it has the most kinetic energy, the most energy of motion. Now, physicists had intuited after a while that like the energy doesn't go anywhere. Well, it goes somewhere, but it stays in the system. Even when you get up to these endpoints here and here and here, even when you get up to those endpoints, the energy still in some sense exists. It's just kind of stored. It's stored in the height of the coin or the ball above the dish. And so we postulate, so to speak, the idea of this thing called potential energy. Okay, and the postulate becomes more reality when you start doing more and more mathematics on it. You realize it explains more and more things, and that's how theories are built, right? Is when you realize that your intuition is actually rigorously describable and explains lots of things. So we have this idea of potential energy, and potential energy is like the stored energy. So when you're up here and the ball has no kinetic energy, the energy is stored in potential energy. Then it comes down, and the potential energy is essentially released into kinetic energy. Then it goes back up, and the energy gets stored again as potential energy. And that's conservation of energy. So the energy really never leaves. You got the same amount of energy all the time. It's just a trade-off. High potential, low kinetic, high kinetic, low potential. It just kind of goes back and forth between kinetic and potential energy. But balls rolling back and forth in dishes are not the only kind of systems that oscillate. So for example, we could have a ball on a spring. And now I've tuned everything just right so that this ball down here on a spring is going back and forth at exactly the same frequency as this ball up here, as this coin in a dish, right? And so the idea here, though, is that also when a physicist looks at this ball on the spring, they're also in their head imagining a hill, a potential energy hill. This is what a ball in a spring might look like to you. This is what it looks like to a physicist, right? So even as that ball is going back and forth, right? So it's got no kinetic energy, high kinetic, so no kinetic energy, no kinetic energy. And then when it's in the middle, it's got high kinetic energy, again, high kinetic energy. And that's because there's this sort of imaginary hill up here where we say, oh, when the ball is at its endpoints, it's storing that energy in the spring as potential energy. And so this is the way we're going to have to look at pretty much everything in this talk, through the lens of energy, potential energy. And we've got this, so the general principle here is that things want to go down in potential energy. Just like balls want to roll downhill, no matter what is moving, we can always think that there's some potential energy field behind it, and things want to get to the bottom of that potential energy hill, but when they do, they pick up kinetic energy, they generally speaking roll up the other side. Let me give you an example of where this concept is useful in chemistry. So here we have a potential energy hill or well, so to speak, But the coordinate down here is no longer just the coordinate of something moving back and forth across the plane of a page. It's a twist angle. It's a twist angle for this molecule. So while in our heads, we're imagining a ball rolling back and forth in the bottom of this well, well, the back and forth motion actually maps onto the twist angle of this molecule. And what we're describing, this is like trying to get dressed in a reverse mirror. All right, there we go. So this twist angle, good grief. Okay, so this twist angle, right, as we're going back, as this ball, this hypothetical fictitious ball is going back and forth in terms of this twist angle, what's happening is that this molecule is oscillating back and forth in terms of its twist angle. So the molecule, for the most part, wants to be, this is, by the way, this is massively exaggerated, right? Molecules don't vibrate nearly with this amount of amplitude. It's a much smaller motion. The molecule tends towards being flat because that's where it would have the lowest energy, but it oscillates around being flat with a small twist. Now, something that interesting that can happen when this molecule is subjected to some light, it can change the potential energy surface. And this is why we absolutely must talk about the potential energy surface, because that is what changes when you expose this thing to light. So you expose this molecule to light right here. The electrons in this vicinity, they completely rearrange. And it completely changes the way the springs that put this molecule together behave. And now, instead of having a minimum that wants to hold the molecule flat, you're at a maximum. So now, rather than the molecule being nice and stable being flat, it is actually unstable being flat, and it wants to roll off of that maximum and become twisted at 90 degrees. And so then, just for fun, I'll show you what that looks like when it vibrates. Right, so it will vibrate looking a little bit more like that. So it's centered. I should have put like some coordinates down here. This is 90 degrees, right? So it's centered at 90 degrees. It would most prefer to be at 90 degrees. But then of course there's just the energy goes up just a little bit when it cocks. And so it kind of oscillates back and forth around being at 90 degrees. We're very, very close now to understanding at least some of the basics of how vision works, but we haven't yet the quantum mechanics. The quantum mechanics comes in answering the question why. Why does it do this? Why is it that when we expose it to light, the potential energy surface changes from this to this? That's the question that quantum mechanics will answer for us by the end of the talk. But before I do that, I'm just going to finish off the story about how does this twisting lead us to see things. Okay. So this is just kind of a summary, right? In case everything else about the energy felt a little bit too abstract, this is the summary. You expose your molecule to light and it goes from being flat to being twisted. This is the protein this is the protein complex rhodopsin, which has a molecule in it called retinol. Rhodopsin lives in the rods of your eyes. So if you'll remember back to, I think it's probably like late grade school when they teach you this, you have rods and cones, right? The rods are super sensitive to light, and their job is essentially to give you dark and light, right? And so when at night, the only thing you can see basically is black and white, that's because your cones are essentially done. They're done for the day, and all you're seeing is black and white, right? And then the cones are the ones that are a little bit more sensitive to exactly which color you're seeing. So this rhodopsin complex lives in the rods of your eyes. And it has this molecule in it called retinol, because that's how scientists often do things. They name things by where they found them, right? Germanium, for example, was isolated in Germany, right? And retinol was first isolated in people's retinas. So this molecule retinol is right here inside the rhodopsin complex. And you don't have to understand all the different stuff on this slide. The main thing you need to understand here is that this thing is crooked. When the molecule is the happiest, it is crooked. It is not straight. But what happens is you expose it to light, it changes the forces around this double bond right there, and the molecule straightens out. So because of the way you change, basically you expose it to light, the molecule goes around one of those double bonds. It goes from wanting to be flat to wanting to be crooked. So it changes shape. The rhodopsin is super sensitive to this. It's like that molecule changes shape and all these coils around the outside go, oh, okay, fine. And then this sets off some biochemical sequence of reactions of which I know nothing about, that triggers like neurons to send messages to your brain and basically, hey, we found a photon, is basically what happens there, right? So when this molecule here absorbs a photon, when it takes on a little bit of light and changes shape, it sets off a sequence of events that tells your body, hey, we found a photon at this location on your retina. Okay. And that, for all intents and purposes, is how we see. But where's the quantum mechanics, right? So let's start another story. So it's almost like this story is kind of coming to an end. We're going to start another story, and at the end, the two stories turn into one story. Okay, quantum particles. We have here just some particle. It's moving. It's going through a detector. This is about the simplest experiment you can imagine. Is there a particle or not? The only reason I've even bothered putting a detector here is just to make it unambiguous. There was a particle. Something was there. Something caused this thing to light up. And now we ask the question, if we could look down at a microscopic level, if we could zoom way in on this particle, whatever it was that caused that light bulb to go on, what would we see? I mean, naively, we might just assume, and this is right around 1900, for good reason, this is what people assumed they would see. They assumed that if you have a very small particle, it looks like a very small particle, like a little ball, right? Just very small, so small you can't see it. But this is, in fact, after many experiments, we realized it can't be like this. There are a couple of good reasons, right? And Gabriella has already taken an exam on exactly what those reasons are, right? There are a couple of good reasons why we know that it can't be like this. Atoms wouldn't be stable. It doesn't explain diffraction patterns of particles, blah, blah, blah. The list goes on, but we're not going to go down that road. After a whole bunch of theory later, we realize if you do this, it looks something more like this. That's a little bit more akin to what you would see. Of course, seeing is kind of hard to talk about, right? These things are actually smaller than wavelengths of light, so seeing doesn't really make any sense. But if you had a theoretical model of what you would see, this would be it. The most noticeable thing here, it doesn't have a clear boundary. There's not a clear edge to where the particle is, like the particle is inside this wall, and it's not outside that wall. It's more like fuzzy. It's like there's particleness, that's a weird word, but that's kind of the way we're going to talk about it. There's particleness, a lot of particleness in this region. And there's not a lot of particleness in this region, which means the particle, to the extent that it is just the sum of all the particleness, is somewhere here-ish. And that's what a quantum mechanical particle is more like, right? Another thing you might notice, you're like, it's striped. Why is it striped? Okay, before I tell you exactly what the stripes are, let me show you what happens if we slow this particle down just a little bit. So the first thing I'm going to do is in the next slide, you're just going to see this arrow here, which is supposed to indicate how fast the particle is moving. It's just going to shrink a little bit, right? So slow the particle down and ask, okay, now what would we see? And I think the first thing we all know that we're going to see is that it's going to move slower, right? I mean, because that's basically the definition of slowing it down, right? So let's go ahead and do that and see what else we can see. All right, here it comes. Yeah. Definitely moving slower this time. And one of the characteristics is still the same. A lot of particleness in the middle. Not so much out here. The particle is here-ish. But there's another huge difference that I would doubt that anybody missed, which is that the stripes seem to be wider, right? The stripes seem to be, so what are those stripes? This thing is a wave. Those stripes are telling you the phase of the wave, which is a kind of a mouthful if you've never heard words like that. Phase is a generalization of the word sign. Sign means positive and negative. All right, so here's a pretty easy association. Green, like go, like stoplight, green is positive. Red, like stop, negative, okay? Green here is positive, red is negative. So it's going from positive to negative, right? Positive to negative to positive to negative to positive to negative, right? That's a wave. Positive to negative to positive to negative to positive to negative, that's a wave. And so then you intuit from this, you're like, okay, I get it. So if green is positive and red is negative, then yellow must be zero because you got to go through zero to get from positive to negative. Not so fast. There are ways of getting from positive to negative without going through zero. That's the whole bit about complex numbers, which I can't get into today. So you're just gonna have to write a little on a box on a piece of paper in front of you, I believe, and go ahead and just push that button, right? You can get from positive to negative without going through zero using these things called complex numbers. But it's nonetheless, you're still going from positive to negative. Red, orange, so basically red, orange, yellow, green, blue, purple, red, orange, yellow, green, blue, purple. You're going between red and green, positive and negative, just without going through zero. Now, the bit about how close together the stripes are, this we call wavelength. So this particle here, compared to the one we just saw, has a long wavelength, because this takes a longer distance to get between two reds or two greens, and it's moving slower. That is probably the most important association you can make about quantum mechanics to follow the rest of the talk. Long wavelength, slow, low energy. Short wavelength, fast, high energy. I'll say that one more time because it's that important. Long wavelength, slow, low energy, right? Short wavelength, fast, high energy. All right, so I'm over it, right? We're over it now. Particles are waves, apparently, okay? Right? I mean, they're not here or there, they're here-ish, right? They have wavelengths, but short or long, but we're over it. Particles are waves. But what does that mean for an atom then? No, I'm getting ahead of myself. Let's cover, it was so important. I have actually a couple more slides about slow, fast, short, and long, right? So let me just remind you of something that I think everybody knows, which is that shorter strings vibrate at higher frequencies than long strings, right? So you have a long string, it vibrates at one frequency, shorter vibrates at a higher frequency, even shorter vibrates at an even higher frequency, right? So it stands to reason, that being the case, that even if you have strings of the same length, then if they have a short wavelength, they'll oscillate faster, right? Short strings oscillate faster, and strings with short wavelengths oscillate faster. So this is again hitting home the point, right? Short, right? Short is fast, is high energy. And in case you would not remember that short and fast go together, let me just remind you, and you can take a nice little pause with this beautiful video. If you're not into Spanish guitar yet, let this be your introduction. What I want you to watch about 2-3 seconds into this video, right? I want you to watch and see what you would see with your eyes and correlate it with what you hear with your ears. I'm going to tell you in advance what you're going to see, because every time I do this with students and then I go through it. So what'd you see? Like, I didn't get it, right? You're going to watch his hands move down the fret, making the strings all shorter, and the pitch is going to get higher. So let's just watch it. Oh no, it's only coming through my earbuds because I'm. Okay. I tell you what, I promise at the end, I'm not even going to try to mess with the technology right now. You know, there are always glitches. All right. It goes something like this. Right. So you guys moves his hand down the fret and it gets higher pitched. All right. So that was a little fail on that technology. All right. So what does this mean for atoms? Right. So we're over it. Electrons move as waves. So then if an electron is moving as a wave and we've got this negatively charged electron and it is being attracted to a positively charged nucleus. So it's like, okay, so the electron is attracted to the nucleus and I guess it's going in around in a circle around that nucleus and it's a wave, and I'm over the fact that it's a wave. And so it's going around the nucleus like a wave does, right? No definite position, it has a wavelength. Okay, but not so fast. It doesn't actually work that way. At least that's not how it stays. There's this thing called radiation. This would give rise to a radiating dipole. It would slowly radiate away its energy. In short, this thing is going to spiral in towards the nucleus. And you can kind of see by the fact that it has a finite volume that it's never going to quite get there, because of the nucleus, as this is actually exaggerated, the nucleus should actually be an imperceptible speck in the middle of this thing, right? And this thing is just sort of, it's much bigger than the nucleus. So as it spirals in on the nucleus, it's never going to quite get there, because the volume that the electron itself, the electron wave itself takes up is bigger than the size of the nucleus itself. And so it settles into this thing that we call a standing wave. Eventually, it occupies a state that just looks like this. It's just sitting right there as kind of an unmoving wave in the vicinity of the nucleus. Not moving in one sense, but moving in another. It's not moving in the sense that it's no longer circling the nucleus. It's not moving right or left. It's not moving up or down or in or out, but there is a certain sense in which it's moving. It's still changing phase. Just like this guitar string goes from positive to negative to positive to negative, this thing sits there and oscillates from positive to negative, back to positive to negative to positive to negative. It's what we call a standing wave. It's a wave that stays in one place going up and down. And so that is what an electron sort of looks like, so to speak, when it's in the lowest possible energy state that it can be in an atom. Now, I didn't show you what's in between because you know there are ways of getting from positive to negative without going through zero, right? But that's coming. Let's watch in detail the evolution of an electron as it's being exposed to light. Okay, so I'm gonna play this video a little ways, then I'll stop it, tell you what you saw, and tell you what you're about to see. So here we go. The first thing we're gonna do, we're just gonna start this thing, and the light is kind of not on at the beginning. So this white bar over here, by the way, that's like the strength of the light field, and you'll see that it's kind of, at the very beginning, it's small. That's the only thing you need to realize, that it's small at the beginning. In other words, it's not being exposed to very intense radiation. So here we go. Oh, red, green, red again, green again. Okay, that's what it means basically to oscillate without, you notice how it never went away, right? It never went through zero. It just kind of makes this color progression. It goes through red and green, but it never goes away. It goes through these other colors, right? And so now what's about to happen is we're turning on the light field. This arrow right here is basically, it's the electromagnetic field. Now let's remember what that is, right? Eons ago, in a light bulb far, far away, some electrons were oscillating. Those electrons were oscillating and they were disturbing the electromagnetic field in the vicinity of that light bulb. Those disturbances have now come and they are now impinging upon this electron. What those are those forces. You have the electromagnetic field act as forces upon the negatively charged electron. So at this point, the forces are pushing that electron upwards. But now I want to remind you something. Think about pushing a kid on the swing. You're pushing a kid on the swing, they come back towards you and you push. They come back towards you and you push. The thing I want to remind you of is you're pushing the hardest when the kid is sitting still. They're right in front of you and they're barely moving, and that's when you're pushing the hardest. When the kid is moving fast, you're not touching them at all. You're going to see the same sort of offset of phase here. It's almost going to look like the electron's doing the wrong thing. You're like, why is the electron moving down when the force is pushing upwards? Well, that's because the electron is moving down, the force is pushing upwards, causing it to stop, turn around, and go up. There's like a phase lag between the arrow that you're going to see here and what you see the electron do here. So you don't need to pay too much attention to the field over here. Mostly just keep your eyes on the electron. It's going to start going up and down as the force from the electric field pushes it up and down. There we go. First, just kind of just sitting there. Now the field is getting stronger. The electron no longer able to resist the force of this field. All right, starting to wiggle a little bit, going up and down and up. And now something weird is starting to happen. Soon, yeah, you see how you can see more than one color at the same time? You're starting to see more than one color at the same time. As a matter of fact, the whole wave appears to be changing shape. If I'm not mistaken, it's starting to look like it's taking on something like a darkness in the middle. Like it's never really quite all that bright in the middle anymore. And at that, the shape that it's taking on seems to be stabilizing now, as if it's getting to some sort of interesting stationary state. And right about here, if we let the simulation go on for a while, it would stay like this for a while until eventually the forces essentially would turn it around and send it back down to being in the ground state. But look at that. The whole wave changed shape. In the beginning, the wave actually had this character. The whole wave had the same sign everywhere. It was positive or all negative everywhere. It's either all positive or all negative all at once. Now it has a character more like this. On one side, it's positive. On the other side, it's negative, right? So the light has changed the shape of the wave-like character of the electron. And that's the last piece of the puzzle to understanding vision. We're one slide away now from putting all the pieces together. So this is the way that electrons are arranged in a carbon-carbon double bond. You don't even have to know what a carbon-carbon double bond is. You just have to know that it's one of the ways that carbon can stick together. You got a carbon-carbon double bond, and this is what the wave-like character of an electron in a carbon-carbon double bond looks like when you've just left it alone for a while. We call that its ground state, the lowest energy state it can be in. When you subject it to light, it changes shape. And this you actually just saw. You actually saw just how this happens, right? You subject this electron to light, it changes shape. In this case, in the last case, everything had the same phase everywhere, and it went for having a different phase on two different sides. Here, this one starts with two different phases, a positive and a negative on two different sides, and goes, and now it has four different lobes. But one of the things this does, one of the ways you can identify that this is higher in energy than this, if you had to assign this a wavelength, it would be shorter, right? As you go along this stretch, as you go across the page here, it's positive everywhere, negative everywhere, and here it oscillates already. Within the distance of the molecule, it goes from positive to negative. So it's basically like a long wavelength versus a short wavelength. So this one's higher in energy. And as a matter of fact, it knows that it can still make its energy yet lower by twisting. That little bit of a twist is just enough to increase the wavelength. It doesn't matter how little. The fact is, it increases the wavelength just a little, which means it puts it down in energy, causes that molecule to twist. That molecule twists, it sets off the chain reaction, right? Knocks around some rhodopsin components and causes us to be able to see. And so that's the story. That's basically the end of the story of how quantum mechanics, that is the wave character of the electrons, underlies the everyday phenomenon of being able to see. As I said, well, hold on, don't clap just yet. I said I had 5 slides left, right, of my own research. But I understand. Yeah, we should still have plenty of time for, just chit chat too, right? Which is kind of the point, right? So as I said, this is not my stuff, right? This is just kind of an introduction to what is the utility of understanding quantum mechanics in trying to approach like everyday problems of relevance, right? So let me give you some idea of what are some of the stuff that that I work on. This is a brand new project, as I've been working on it for like 2 semesters, and it goes a little bit too far to say this is my research. If anyone owns this project, it would be Dr. Harrison in the chemistry department, in terms of like envisioning like what is it that we're going to explore, what do we hope to find, all that kind of stuff. If anybody owns this project in terms of who did the work, it's Nina Sun, who's sitting right here. And I wish, if I was giving this talk like 1 week later, I would show you the data that she says hot off the press, but like I was just like walking out the door to come give this talk. I was like, yeah, that's really cool. That's what we wanted to see. Like, that's kind of like right where we are right now with it. But let me just kind of give you an idea of like, what this project looks like. Deep, 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 deep in the heart of a protein. You can tell it's a protein because there's just way too much stuff going on for the likes of somebody like me, right? There's just too many atoms. And that's like, I'm not comfortable, Dr. Harrison is comfortable. And so I'm like just holding his hand as we go through this project, right? But deep, deep, deep in the heart of a protein, there's a chemical group that's made of 1 nitrogen and 2 hydrogens. And it is attacking, and we actually use that word in chemistry, it is attacking another chemical group that is made of 1 carbon double bonded to an oxygen, okay? That schematically, right? So this is how a chemist looks at things, right? And then it's like, it's all really overwhelming because there's just way too many atoms, right? And so biochemists take care of that problem by drawing their pictures like this. They just summarily get rid of all the atoms, draw squares and circles, right? And so basically what's happening here, when the NH2 attacks the CO double bond, what happens is this whole thing called ubiquitin gets transferred over to the green block and it tags it. So this is one step in a chemical process of tagging a substrate and saying, ha, now you've got a ubiquitin stuck to you, right? And it's called ubiquitin because it's everywhere. This is like one of the primary molecules that are used to tag things inside of a biochemical pathway. And why do you tag things? Well, sometimes it's to regulate their activity. So another molecule comes on and says, hey, oh no, you're tagged. I don't think we're going to give you the substrate you want because, you've been downregulated. Sometimes it's tagged for repair. Like the ubiquitins, actually, they can form chains and branch chains. There are all different ways to tag things, right? Sometimes it's tagged for repair. It's like, oh, okay, I see you're in need of help, right? Sometimes you're tagged for degradation, like everything, right? Has a usage lifetime, planned obsolescence, if you like, right? And then it's like, okay, I see that you're tagged for destruction. Come on, buddy, right? So this is this is ubiquitous. It's everywhere, and it's used to tag molecules. But not a lot is known about how this step happens. Right? It's like this particular step right there, when the tagging happens, right? That's not a very favorable approach right there. And so it's probably got something to do with the torsion angle around that sulfur that makes it more or less favorable. And that has to do something with the way the protein environment kind of bends it over its knee while it stuffs the NH2 in there. And that's what we're trying to figure out. Okay. That is like one of several projects that I'm trying to get up off the ground here, so that basically I can, be useful, right, with, undergraduates who, want to like look at biochemical kind of pathways. And, basically we need semester and year-long projects, right? I have a longer running passion, which I've kind of realized like I'm going to have to move very, very slowly on it, because I was naive when I first got here. I thought I could chop this thing up like salami, like really, really thin, and piece it out to undergrads. It's just too hard, right? That's just the long and the short of it, just too hard. But it's still like where my heart lies. And so I'm going to tell you just a little bit about what it is, because I'm still working on it, right? It's a mouthful. You don't even have to say these words. Just know that this is the name of my baby, right? It's older than my oldest son, right? And so this is like my, my theory that I'm developing, right? And what it is, it's a method to handle the quantum mechanics of tens of thousands of electrons and here's the key words. This is like, you have cliques inside of science, right? Inside of science, there's like certain groups that have like a certain mandala or mantra. This is like what they do. And then it's just like, the Sith, right? You bring in somebody new and you train them in your ways, right? So when I was brought in to science, the mandala for us, systematically improvable accuracy. It's the only way that you know when you're getting the right answer. You could try this method and that method and that method and that method. And if they don't agree, what do you got? A mess. You don't know what's right. But if you have a method that you know is guaranteed to approach accuracy as you turn the dial up, even if it's highly theoretical that you basically can't afford to do that, at least in theory, if you could afford to do that, you'll know you have the right answer when it stops changing as you turn the dial up. That's how you know. It's the only way you can ever know that you have the right answer in simulation science. The key is to make a systematically improvable method cheap enough that you can actually turn the dial up. That's the hard part, right? It's nasty. It's not all fun and games. This is why I don't give it to undergrads anymore. So, but I love those equations. Like that's kind of what, like, when you realize you're like, I'm weird. Like nobody else likes these the same way I do, except for maybe Chris. He probably looking at those like, what are those? Right? Anyways, okay, what's this useful for? All kinds of cool stuff. I'm only like 2 minutes from the end here, right? Just these are just some 4 categories of problems we might try to solve in order of increasing complexity. One thing you might say is like, well, sometimes you just need binding energies, right? Because the equilibrium constant, that is basically the proportion of whether you're on or off, right? That's what the fancy word for equilibrium constant is a fancy word for just the proportion of whether you're on or off, bound or not bound. It depends exponentially on the energy. Small error of the energy, huge error in the equilibrium constant. So sometimes you have a big system, you just need really high accuracy. Yeah, okay. I mean, if that's the first thing we got to do, so be it. But that's boring. All right. What about something a little bit more interesting? What about you have some huge protein matrix, lots of different things going on, lots of different charges around, and maybe an ion over here, and there's just like tons of stuff going on, and there are bonds breaking and forming. Now, when bonds break and form, the electron dance gets really complicated. You can't make a whole lot of approximations that don't damn your answer right from the start. So, that's a little bit more fun. All right, not fun enough, right? How about cases where the electrons are actually explicitly not in their ground state, right? What about cases where you definitely have to handle the quantum mechanics of the electrons in a quantum mechanical way because they're actually being excited out of their ground state into a more excited state? So that might be something like these experiments, which I'm not going to explain the graphs, right? The only thing about this that you should be looking at is, there's some solute here, there's a bunch of molecules around it, then we've made some excitation of that thing, and the electrons have changed their shape, and we want to know, how does this affect the solute molecules, and how do the solute molecules affect it? And a lot of this is basically like just using this atom to get at what the solute dynamics are, so that we can understand like how things get solvated in solution. And all right, so what about the big kahuna? All right, we've had a case where electrons are in their ground state, but we just want high accuracy. Then maybe they're in their ground state, but bonds are being made or formed. Maybe they're not in their ground state. Maybe they're not even staying still. Maybe like in the redox chain for respiration, you've got this situation. The redox chain in respiration is basically biochemical circuitry. It's one molecule passing an electron to another molecule, passing an electron to another molecule, passing an electron to another molecule. And all along the way, as this electron gets lower and lower and lower and lower in every step of the way, it causes this chemical reaction to happen. It causes that chemical reaction. It causes that chemical reaction. And that's how we take the energy of the sun and get usable chemical energy. Basically, you know this from being able to burn wood. When you burn wood, you're releasing the energy of the sun. That is energy of the sun that has been stored in chemicals, and now you're taking a match to it and letting it out, right? So respiration is a situation where the respiration chain is a situation where the electrons, they're not in their ground state. They're doing a complicated dance. They're not even just in their excited state, they are moving. They themselves are moving, and if you don't handle that in its full wave-like glory, you've got no hope. Okay, so that is the end of it. That's kind of like a little bit of an overview of where quantum mechanics fits into everyday processes and the kinds of things I'm interested in researching. And yeah, I think we have plenty of time to chat and take questions.